People studying lightning get all excited about the possibility of getting 10 kilovolt X-rays out of lightning, and here we can peel tape and get 50 kilovolt X-rays out of peeling tape.
At the University of California, Los Angeles, Seth Putterman, Carlos Camara, and Juan Escobar, with their colleague Jonathan Hurd, have been releasing some of the energy locked up in the surfaces of things.
You'll see electrons some of the time looking as though they're in bound states and some of the time looking as though they're whizzing around. Sometimes the surface will look like it's insulating, and at times it will turn into a conducting surface due to stirring up all the ions and electrons. We've been very much interested in natural phenomena that concentrate energy density. In the 1600s, it was discovered that when you scrub mercury against the walls of a barometer tube, flashes of light come from where the mercury meets the walls. And it turns out that this is due to spectacularly catastrophic events at surfaces of interaction.
In Russia, in the 1930s, Abramov suggested that splitting mica might produce bursts of energy. And in the 1950s, Karasev first suggested that peeling tape could produce X-rays, though few believed him at the time.
It would be a fantastic energy-focusing phenomenon if by peeling tape or splitting mica, you could turn the small mechanical force required to split the mica or the small force required to peel tape into X-rays. And so basically we said, this is too good to be true. We want to see it for ourselves.
I personally got involved for exactly that same reason. I did not believe it. As we know, when we rub a comb through our hair, we can then attract little pieces of paper. That's because charge has been attached to the comb from our hair, and the opposite charge has been attached to our hair.
And in a Van de Graaff machine, rubbing surfaces produces a similar effect.
So here we have spectacular discharges between the charge accumulating there and ground over here. It's probably generating X-rays. And then you have a mechanism of discharge, which is in the case of a lightning strike, is the field, the energy has become so enormous that there is a breakdown and the air becomes conductive and all these electrons rush down and discharge.
You can get voltages of 300,000 volts. And we had heard that adhesives could do something similar, and we didn't believe it at first. And so, for example, if you have just tape and you open it, you see that it's charged, right? So it can move towards my hand because of the charge that is left. We also heard that it was possible that that would generate X-rays.
So this is our vacuum chamber. And as you can see, we just go from one reel to another reel. There it is, and now you can see the motor go off. Here we have the tape, it's getting unrolled. The scintillator, sensitive to high energy electrons. Now we're going to turn on the vacuum and remove those gas particles from around the tape.
The experiment has to be in vacuum, because if it's not, then you will have gas particles around it that will make the surfaces discharge before you can separate them to a point where the potential is large enough to generate X-rays.
We're going to about the pressure that 1,000th of a millimeter of mercury would have under the force of gravity on Earth.
These are electrons, as the tape is peeling, are being ejected. And it's those same electrons that, when they hit the other side of the tape, are going to generate the X-rays. So this is a Geiger counter, and we're going to see if we turn it off for a second.
Okay.
There's actually nothing there. But as soon as you turn it on,
you are seeing the needle go up, huh? Yeah. Now the motor is actually not peeling the tape that fast. We're peeling it at about, say, 5 centimeters a second. That's really, you know, about this fast. So it's not like we're really ripping it with tremendous force. And yet there's enough charge there and enough discharge of electrons that this enormous flux of X-rays comes out. Enough, actually, to our surprise, to take an X-ray picture with peeling tape as the source.
What we have over here is X-ray film. And it's very simple. With this same setup, you can put your finger and then put the X-ray film on top. And then maybe take another one and do it on this section of the finger, and then another one on this section of the finger. And then when we develop the film, you can actually see an image of the finger.
This is the same X-ray film that is used by dentists. Now there you're connected to an enormous X-ray machine. In fact, the dentist usually leaves the room while they fire it. And here we have a remarkably simple alternative to that, which is capable of developing the same film. And we've looked at it with a microscope, and it's really messy. There are all these filaments. It's a very complicated process. This gooey thing unsticks.
I find it amazing that you've got this complex tangle of strings at the vertex of the peeling tape, which is about 100 microns in this picture. And out of this complex motion, you get a collective blast of 100,000 X-ray photons in merely 10 to the minus 9, a billionth of a second. I don't understand how such a cooperative phenomenon takes place.
This is the cheapest way to generate X-rays at this scale.
And then you could have these devices in third world countries where electricity is a very expensive commodity, where it's not that easy to get an X-ray.
What you're seeing here today is what we got with the first roll of tape that we used. I propose that by studying various adhesives and what's going on and learning what's happening here, improvements of a factor of 10 or 100 could be made.
So now, especially for Nature Video, today they're trying out a new type of tape.
So let's give it a whirl.
Okay.
Does it have a different feel to it?
Not really. It really looks about the same. Okay. Well, there you go.
There's light at least.
There's a lot of light.
A lot of light.
Maybe it works better. Yeah, it never fails to amaze me.
Okay, now turn it on. I'm getting scared.
Let me do it. Let me do it. Yeah. And it's coming right from the vertex. You see that?
Yeah.
Maybe we got our factor of 10 right here.
Oh, it's amazing.
This is very bright. That's incredible.
Bye.